Hello everyone. Sorry for not being there actually. So I had some problems with the train connection because of the harsh winter weather in Germany. My train connection was cancelled, and so was my flight connection. So that's why I'm here just remotely. And so in the next 50 minutes, I'd like to give you some insights into work that is going on towards safe autonomous robots. And of course, we'll also show you how this links to the RoboSAPIENS project, which was just presented by Peter. So before I start, my name is Roland Behrens. I'm with Fraunhofer. So I have a background in mechatronics. I did my PhD a long time ago on the topic biomechanical limits for safe human-robot interactions. And besides my role here at Fraunhofer, so currently I'm leading a department called Human-Centered System, which is also working on safety solutions. And beside this role, I'm also convener at ISO, and more precisely ISO TC 299 WG8. And WG8 is the group which is working on new standards for safe human-robot collaboration. Good, so that's should be all to my person. So let's dive into the topic. So when we talk about robots or even collaborative robots, cobots, we can say that we have three possibilities in order to safeguard or protect humans which are working around the robots from these robots, from collisions. So on the left side, you see a very simple approach, and this is a common procedure since decades, I would say. So just separation. You just put a fence around the robot and everything is fine. The robot can do whatever it wants inside the fence, and the people are just protected by simple separation. So not very exciting, I would say. And over the last years, we can already say a decade, we saw that new approaches emerge from standardization. So in the middle, we see collision avoidance, which is a very simple approach. So we try to keep a safe distance between the moving robot and a human. Whenever a certain distance is violated, so when there actually the human steps too close towards the robot, then the robot just stops. So they are with this safeguarding mode, with this safety method, we avoid that the human is actually able to touch a moving robot. So we call this speed and separation monitoring, or SSM. So this is the term which is used in standardization in order to refer exactly to what I just said. So and then we have on the right side collision management, and this is the idea that we can actually touch the moving robot. Or that we can get into physical contact with it as long as certain biomechanical thresholds are not exceeded. So biomechanical thresholds are mostly forces and pressures which the robot should not exceed during a collision. I think it's clear that whenever a force reaches a certain level, we can probably cause injury, and injury is forbidden, at least when you're using a cobot in an industrial setting. So this should be avoided. And so these limits that have been set by standardization, they avoid exactly that someone can be injured. And this safety method is named power and force limiting. At least that's how it's treated in the standardization domain. Okay. Good. So these are the three general concepts. So what does it actually mean for robotics in general? So in order to show you the gravity or the importance on power and force limiting, let me introduce you to this taxonomy. So on the left side, we see very simplified but very relevant characteristics of an industrial use case. So often the question is, do we need a shared workspace? For instance, do a person need actually to work together hand in hand with the robot? So then another characteristics would be, is the work simultaneously? So do they work at the same time in the same workspace? Is this really necessary for the process? And another feature or another characteristics would be, do they actually need to work hand in hand? And so if you can say yes or no, so if we do like a decision tree here, we end up into different forms of interaction. Let's start with coexistence. Coexistence means there's no interaction at all. So we don't have a shared workspace, we don't have simultaneous work, or we don't have this working hand in hand. But let's assume we have shared workspace. Then the question is, do we have simultaneous work? If not, it's sequential cooperation. If we have it, it's parallel cooperation. And if the robot is actually needed to work hand in hand with the humans side by side, then we have collaboration. Okay, what does it mean for the safety method I have just introduced? This means, or you can see it on the right, power and force limiting can be used for all forms of interaction. So of course we can use fences for coexistence, but coexistence or fences will not work for when I need to work simultaneously in the same workspace with the robot, because then fences doesn't make any sense. Same applies to the speed and separation monitoring. When I actually need to work side by side, hand in hand, power, speed and separation monitoring, so actually avoiding collisions, that's not usable. So it does not work, it's not applicable, and that's why we have here only left power and force limiting. But what we see is that we can use power and force limiting for any form of interaction. And this is kind of the reason why this attracts the most attention. So when we are able to safeguard a robot with PFL, we can use it for any application, for any form of interaction. And that's why it's so important in industrial applications, but also for using robot in service applications. Good. So the thing is with power and force limiting, I said already, so we need to comply with biomechanical thresholds. And the question might arise, okay, how do we do this? How can we ensure that the robot complies with certain limits? So state of the art is actually pretty simple. We do testing. So we do collision tests. And you see it here in the video. I hope it's streaming well. So it's very simple. It's a slow motion video recorded at 100 Hertz. So we have this device. We call it the pressure force measurement device. This one here on the right, which is mounted on a larger robot. It has a cylinder. Inside the cylinder, you will find the load cell, which is measuring the forces. And on top of that, you have an impactor or the bumper, which is actually taking the force. And here we have damping material. And what we do not see, but here inside, there's a spring. And the combination of the damping material and the spring is selected in a way that it kind of mimics, the human biomechanics, the human compliance of the soft tissue. And then we have to install it in the application, and then we have to go with the robot into the measurement device. And then, of course, we measure the forces, we measure the pressure, and then we can compare the results with the limits. The problem is with this device, it requires a lot of effort in order to organize these measurements. Let me start the video here again. So it looks very simple, but it takes a lot of time and money in order to arrange the systems, to program the robot. Then we have the problem that the measurement device is too large. We cannot install it in narrow spaces, and so on, yada, yada, yada. But the most important thing here is, of course, the measurement approach does not work for autonomous robots. So whenever a robot is able to take its own decisions to decide what to do next, you cannot check if this action, this movement is safe within the given biomechanical framework. So we cannot do a testing and then allow the robot to apply actually the movement. So measurement is out of the game. It does not work. But this also means we need option B. So we need an alternative for the measurement. And this brings me to my next slides. But before that, there is another topic or another problem which actually triggers today industries. So whenever we do the measurement, we can do it at the very end, after the robot was designed, after the robot was installed, after the robot was validated regarding the risk it might imply, and so on and so forth. And then we do the testing at the very, very end. So everything is done. And then we realized after the test, oh my God, this doesn't work. So we have to go back to the start because we exceed the limits. We need to reduce the speeds. We need to redesign and so on and so forth. So this is a nightmare. This triggers people which are actually owning companies, because this costs a lot of money. So the expectation at the beginning was I can end up with a robot that's actually doing some work. But when I just realized with the test, it doesn't work, this is too uncertain. The risk is too high to take, because we don't know what I will receive at the end as a company owner or as an entrepreneur. Okay, so what we actually want is, okay, let's do some simulations, and during the simulations we also try to simulate what could be the forces in a collision. And whenever I find a proper, let's say, design which fulfills on one side the economic goals, but also the safety requirements, and here most and foremost the biomechanical limits, then I can decide to take the next step, because then I know, okay, I've done my homework, I see it will work at the end, and I can actually go over to purchase everything, to install it, to program it, to do then probably a path validation based on the same simulations, and then I'm free to go. So there are no surprises, and this is a straight way towards a productive operation mode. And of course, this also works for autonomous robots. So we can use the same algorithm, the same software we're using here at the very beginning, or for post-validation during the operation. Whenever the robot decides it has to be reconfigured or it has to take a different decision, and then I can just using the software, doing the validation, checking if it's still comply with the limits, and if so, it's free to go, free to operate. Good. So how does it work? Let's take a look under the hood. So we need, of course, software. We need models. We need certain technologies. So let's start with the digital risk assessment. I will make this very quick. So this is a standardized procedure. This is carved in stone because it's written in the European machinery regulation. So here we have to collect several information, but these information are actually very relevant for us to do some simulations. So to simulate the collisions that can occur. So, and then of course we need models, and here we need a human model at least and a robot model. No surprises here, I think. So we need a model which actually mimics the human biomechanics, which can be used in simulations, and the same applies for a robot. The good news here is robot models are state of the art since decades. Human models are not, but we're working on this, and we are almost done, almost finished with our work here, so that we can say, okay, there is a human model which can be used for exactly this application. But let's say we have both models, and we can use the models and reduce the complexity to a very simple collision model, which can be easily solved. And this will be important in the next video I will show to you. So let's not take a deep dive into the model. It's a very simple 3-mass oscillator, not very special. And but this is sufficient, I would say, to do a good estimation of contact forces. Okay, so now we know, we have an idea how it can work, and now let me come to the RoboSAPIENS case study that we are leading. So what you see here is, let me start the video. It's a very simple machine tending application. So we have a robot which is actually putting parts in a milling machine, and you can see here my colleague is stepping towards the workspace from the right, and the robot just stops. It's of course very stupid. I mean, it gives you a little bit of flexibility. You don't have fences, that's fine, but the robot still stops whenever a person enters the workspace. And of course, stopping the robot, this costs money. So, and our idea in the RoboSAPIENS project was, okay, let's use the Maple K approach. It was just presented by Peter without giving any details, but use it in order to adapt actually the robot whenever a human is, for instance, too close. And that's what's happening in the next video, or what you will see in the next video. So what we have done on top of that is that we have implemented the model I've just presented inside the robot control unit. So it's working actually there. And now the robot, or the Maple K loop, is able to switch between models and switch between safety requirements. So what you can see here is, it's again my colleague who stepped into the workspace, and you see he's too close to the robot. And whenever he's too close to the robot, then we're switching from collision avoidance to collision management. So, and this gives us the ability not to stop the robot, or we can just avoid to stop the robot. So the robot is just continuously working, of course, with different speeds, but it's not stopping. And here the MapIK loops helps us in a very structured way to switch between the models. And here on the right, there are some other examples from the same case study. So we're stepping into the workspace, the robot continues the work, of course with different speed, but it's still continuing. So it's not a shutdown what we will see. And we also will see here, so this video on top is the robot is going a little bit slower than programmed, and this is managed by the MapIK loop. So the robot is not stopping, it's going very slow, very slow. It's complying with the limits in case it will contact my colleague's hand here, but it continues to work. And this is I would call it a breakthrough for industrial work settings, because that's not what we see today. Good. So what else do we have? This is just an outlook. Of course, in the long run, we want to go further. Now we're talking about collaborative safety, but I think the future is safety intelligence. So using the MapIK loop approaches, using the models, the safety models, combine them, even making even deeper integration, also using it for AI will give us something, or we can end up in a so-called safety intelligence, which is actually an embodied safety AI whatsoever, which gives robot the ability to think about what actually they can cause to humans when they're working around humans. And here I brought some videos. I mean, they look really funny, but they are actually not. So we see humanoids in the past which go just rogue, because of a malfunction. And you see, it's very dangerous, and that should not happen in the future. So humanoid, as I wanted it at my home, should be have an understanding of how vulnerable peoples are, and it should act properly whenever the requirements change. Whenever my kids come into the room, the robot should acknowledge that and should act properly. And I would say it's the future. And with that, I'm done with my presentation. And yeah, thanks for listening.